तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, last two lectures we discussed and seen how powerful the compound semiconductors can be. In fact, in that connection we took a closer look at the binary and ternary compounds, and in ternary compounds we have seen that we can combine different 3-5 semiconductors to achieve band gaps from one range to other range. In fact, you can get direct band gap, indirect band gap. You can also make light emitting diodes, you can make detectors of the wavelength which you look forward to. Now, today we will just take a look at further closer look into this device, this material, especially gallium arsenide and indium phosphide, because we have seen that these are the two materials, that is gallium arsenide and indium phosphide. These are the two materials which will be suitable for microelectronics, and of course, it can be in combination with other materials like aluminum arsenide, gallium phosphide or indium arsenide. We can achieve other applications which are optoelectronic applications also. Now, let us just take a look at the crystal structure. This structure is the cubic structure. In fact, when you say cubic structure, to recapitulate your memory, you can have a simple cubic structure. In the cubic structures, you can classify them as simple cubic structures. If it is a simple cubic structure, that is the unit cell. So, in a crystal structure, what we are defining is a unit cell, which in this case turns out to be cubic structure, and this will be repeated in 3 dimensions, x, y, z directions. That is why we take a look at the single unit cell, because it will repeat itself in all directions. Now, this unit cell can be, I am just keeping it general first, that can be simple cubic. If it is simple cubic, it will have a cubical structure with atoms only in the corner of the cube. It can be, that is okay. It can be face centered cubic if there are atoms in the corner, all the 8 corners, plus atoms at the center of the face, each face. That is, there are actually 6 faces. That will be face centered cubic. You can also have body centered cubic. A body centered cubic is there is an atom at the center of the cube. So, simple cube, face centered, body centered. Now, what we are taking a look at now is different from this. If you are talking of silicon structure, that is diamond structure. A silicon structure is diamond. And gallium arsenide is zinc blende. Structure. Basically, both are same structure. In fact, if you see this simple, this particular cube, it is, if all the atoms here inside the cube and on the cube edges, everything, if all of them are silicon, that is diamond structure. In the case of gallium arsenide, you can see this is the zinc blende structure. In the zinc blende structure, you can see all these black ones they are the arsenic atoms, and all these open circles, in fact you see the 4 of them, they are gallium atoms. Okay. So, the structure is on all these corners of the cube you have arsenic atoms. On all the face centers, top face, the xz plane center, the xy plane center, then this plane, this is yz plane, okay, parallel to yz axis, yz plane, this also center. So, on all these face centers you have got arsenic atom, on all the edges of the cube you have got arsenic atom. Okay. Now, in addition to that you have got these 4. So, for example, this is not inside, this is on the front face. So, this gallium atom is located within the cube of this cell. All these 4 are within the cube. Okay. They are not body center, they are in the cube. The location of them, you can see I have marked the coordinate here. This is the center of coordinates, and from there you move a by 4 in x direction and y direction, move up a by 4. So, if you have the corner there, a by 4 and somewhere here, that is the atom. And you can see similarly there are other atoms which are with respect to the corner a by 4. You do not have to memorize the structure, all that you remember is arsenic atoms all the corners, arsenic atoms on all the face centers, gallium atoms inside, and the 4 gallium atoms, and all the 4 of them are, each one of them is located, for this one is located at a by 4 from that corner. What you do is move exactly diagonally opposite there on the same plane, from that a by 4 here, from here a by 4 up, but the coordinate turns out to be with respect to that 3 a by 4 with respect to xy plane, it is a by 4 raised. So, these 2 atoms are raised from the xy plane. If you take this as the ground plane as the xy plane, a by 4 on those 2 corners. Now, next atom you can, next 2 atoms you can identify, just move around like that to the opposite diagonal. So, as far as this diagonal on the xy plane is concerned, a by 4, move into the opposite diagonal, okay, here. Now, there are no atoms a by 4 from these 2. You move to the top. From the top, a by 4 downwards. From the top here, a by 4 downwards. So, to see, if you imagine this room, you can see that these 2 at the bottom, a by 4, turn around to that, go to the top plane, a up, come a by 4 down. Those are the atoms. That is the zinc blend structure. The ones which are inside a by 4, the 4 are gallium. If it is silicon, diamond structure, all these atoms are silicon, structure is the same. Okay. Now, one more thing that I want to point out here is, there is no sanctity about saying the atoms in the cube are gallium and all on the surface are arsenic. It can be other way also. It all depends where you have taken the center of coordinates, because this keeps on shifting. You can draw the entire diagram just by shifting by a by 4. You will get all the gallium atoms on the cube surface, on the corners and on the face center, and all the arsenic atoms inside. That is the nice thing about it, okay? Because the structure is entirely repeating all over. So, you will have what I have shown here is the ones which is inside. I have shifted up this coordinate, move there, immediately the whole picture will be different. This will move to the corner, all this will move to the corner and the face center, gallium. So, please understand that there is no sanctity about just telling it will always be arsenic atoms on the surface of the cube, gallium inside. It can be other way also. I am repeating once again to make it clearer. Okay. Now, these pictures we will try to also understand if you are not familiar. some of those planes, what arrangement of atoms are there in the planes, all that. Now, if you take this gallium atom, that atom which is located from the origin at A by 4, A by 4, A by 4 up, let us take a look at that. Because if you catch hold of one gallium atom there, the picture of other things are same if I move the center of coordinates. Okay. Here you can see these are the lines which I have drawn, because gallium has got 5 valence electrons. This is the difference between silicon and gallium arsenide. Silicon has got 4 valence electrons. Okay. Now, here on an average, therefore, for gallium and arsenic there are 8 like in silicon. So, this structure also is forming covalent bond. This also forms covalent bond like silicon, but in addition to that there may be slight ionicity because of slight negative charge, that we will discuss later. Right now we will see. So, on an average, since there are 4 valence electrons, this gallium atom forms covalent bond with these 4 neighbors. And who are these 4 neighbors? They are arsenic. And if you take arsenic atoms, who are the neighbors? Gallium. Okay. So, this gallium atom, which are the neighbors? One at the corner here, okay, and other, you can see the solid lines drawn, and the other one is here. That is the, we will go to this room and see the structure will become clearer. That is this phase. One is at the corner, the atom closest to that corner here. The neighbors are the one right at the corner, then other 3 are the ones which form that corner, that is that phase, this phase and this phase. So, that is why if you go to this phase, bottom phase, you can see that is the center of the bottom phase, and if you go to the back side, okay, onto the this side, back side, if you see that plane has got, that is the center. Okay. X is 0, A by 2 is y, A by 2 is z. In fact, the coordinates are marked for you to make it easy to visualize. Okay. Similarly, this one. So, 1, 2, 3, those are the planes, those are the 3 planes which form that corner. So, the atom sitting in that corner forms bond with this atom here, A by 4. It also forms bond with those center atoms, that is the nearest neighbors. You can see any one of them, for example, here, that is coming from that corner down. So, that you can see it forms bond with this nearest neighbors, that corner, and that corner is formed by the top plane and the side 2 planes. So, that forms bond, that forms bonds with those atoms. This is at the back side, this is at the top, this is at the side. Okay, now we can, hereafter you can sit down and visualize that. Okay, this is the structure, thin plane structure. Okay. Now, let us take a look at further. In fact, these will be lying on the main diagonal, these atoms, when you go up from here to there. Let us take a look at the, what are the different planes. Okay. I just removed all other atoms now from that cube, same cube. Okay, it is the same cube, cleaned up everything, I have retained only the top surface. If you take a top surface, that I have marked it as 100 plane. Strictly speaking, it is not 100 plane. Okay. So, the Miller indices, for example, if I take x, y and z, what we are taking is, see, this is A, that is A, that is A. If I draw a plane parallel to that, that is that plane, what you put there on the top. Okay. It intersects this z axis at A, or you call it as 1. If you are putting A, you call it as 1. It intersects the z axis, this plane. Okay. There is something here. this is just to go back to the discussion, intersects z axis at A, call it as 1, normalize with respect to that, y axis at infinity, z axis, I am sorry, x axis at infinity. So, actual coordinates are 1, infinity, infinity. Now, the Miller indices, that is you refer to that plane by what is known as the Miller indice. The Miller indice of this plane is 1 by 1, 1 by infinity, one divided by 1, 1 divided by infinity, 1 divided by infinity, which actually is I am just sorry, this particular thing is different. Write it again, x is 1 by infinity, y is 1 by infinity, z is 1 by 1. So, this plane actually will be equal to 0, 0, 1. But I have called this as here 1, 0, 0 plane. Okay. That is because you take any one of them, the atom arrangement is the same thing. I can make this 1, 0, 0 if I shift the coordinates, center of coordinates. So, what you do is any one of these sides of the cube, parallel to x plane, y plane, z plane, you call it as family of 1, 0, 0 planes. Okay. So, these are the 1, 0, 0 planes. It can be 0, 0, 1, 1, okay, 1, 0, 0, okay, any combination of that, 0, 1, 0, depending upon which one you are looking at. Okay. Now, here this I am sure you have done in your previous course on technology, some of you, but those of you who did not have exposure or have forgotten, I am just recapitulating the thing. Now, you can see here this plane, if you take silicon structure, you go that is having silicon, next plane this gallium plane is at a distance equal to the distance between this plane and a plane crossing through that is equal to a by 4, because all the atoms are located a by 4. Okay. And if I take here for example, that is a by 4 down, this is center, that is a by 2 from top. So, the distance between the planes there 1, 0, 0 family is a by 2, a by 4, a by 4, a by 4, and you can see also the alternate layers are consisting of arsenic, gallium. You can go back to that and see arsenic in that plane, gallium in that plane, arsenic in that plane, gallium in that plane. That you have to sit back and visualize again. Okay. So, you have gallium, arsenic, gallium, arsenic, gallium, arsenic, alternate planes, whether I go this way or that way, because it is all symmetrical. Okay. That is the difference between silicon and gallium arsenide. Silicon will have silicon, 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 nothing else. Okay. Now, let us take a look at this plane. You have see another, I am deliberately going through this because each one has some specific properties, because it is not silicon, 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 it is arsenic, gallium, etc. So, if you take a look at this, what you have marked here is, now I do not have to go to board. This particular plane intersects the x axis at A and y axis at A, z axis at infinity. So, this is 1, 1, 0. Inverse of 1 is 1, inverse of 1 is 1, inverse of infinity is 0. So, this is 1, 1, 0 plane. Okay. And this actually cuts or intersects the 1, 0, 0 plane. The bottom is actually 1, 0, 0 plane. Now, I am calling it, I do not, we are not really distinguishing between 0, 1, 0 and all that, call it 1, 0, 0. Okay. If you cut any one of those planes, property will be same thing, because arrangement of atoms is same thing there. That is why you call it as family of 100. Similarly, you call it as 110. If I draw a plane perpendicular to that way, it will intersect the x axis at A, and y axis, if I go other way, it will intersect at minus A. So, you call it as, you do not call it as 1 minus 1, you call it as 1 bar 0. 1 1 0 if it is like that, like this. If I have a plane going like that, minus A with respect to that coordinates, it is called 1 bar 0. There is no sanctity in that, because the property of that plane and that plane is the same thing, because arrangement of atoms is same thing. You can see here, the arrangement of atoms is actually top plane, top surface, arsenic, 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 and you go diagonally down, you see those 4 atoms which are actually 2 atoms which are A by 4 down, A by 4, A by 4, A by 4. That is that atom, and that atom forms bonds with the nearest neighbors, and it is in the same plane as this. If you take a look at this particular plane, this atom lies on the diagonal. So, that is here, that forms bond with this and this. There are 4 bonds. Other 2 bonds are, that atom forms bond on this plane and also on that plane. That we are not showing, because we are seeing only that particular cut view of that particular plane. Okay. What we are seeing is, marking is only this. Just to take a look at the atomic arrangement, what we are doing is like that. That is the 1 1 0 plane. Arsenic is there, arsenic is there, arsenic is there. That is there. Arsenic here at the corner, arsenic here at this point, bottom plane. Then there is a gallium atom here, there is a gallium atom here. That is the atomic arrangement. Number of atoms you can count there. So, this forms bond here like this, bond here like this, bond here like this, bond like this. Okay. In fact, I should not put this thing, this is only just, bond is only there. This is the boundary which I am marking. Okay. I am drawing by dotted line to distinguish the actual bond and this boundary. So, you have got the arsenic, 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 gallium. You have got the diagram there. Okay. So, this you can see, this particular structure has got certain peculiarities. The gallium atoms are there on the plane, and this gallium atom belongs entirely to the gallium through the plane. This arsenic atom belongs to this plane. It is also shared by the plane which is continuing on the top. So, if you take this area here, contribution of this arsenic plane to this arsenic atom to this plane is half, and this one is 1/4. So, 1, 2, 3, 4. So, 4 together is 1 contribution. This is half, this together is 1. So, actually if you see this particular area, there are 2 gallium atoms, 2 arsenic atoms, pakka, neutral, there is no problem. Okay, that is what I want to point out here. This is a neutral plane, even if there is some charge. In fact, because gallium has got 3 and arsenic has got 5 electrons, there is some ionicity. The bonding is not perfectly neutral like in silicon. There is some shift of electrons towards arsenic actually. So, there will be gallium will be slightly plus charge, in fact it is plus half, arsenic will be minus half charge. So, the bonding between the 2 atoms, the not merely covalent bond, it is also ionic bonding. There is slight force of attraction between them, plus and minus charge. And if you take this plane, whole plane as it is neutral. There may be charge sharing between them. Okay, now let us take a look at it further. this gives further idea about the crystal structure. So, for example, let me just remove this here. So, what we are trying to see now in that picture is the one which intersects here, here and here, the plane. Okay. That is this plane. We have marked it there. Okay. That is A and A. So, this plane is actually intersect is 1, 1, 1, inverse of that also is 1. So, that is 1, 1 plane. Now, when we say 1, 1, 1 plane, we mean the entire family. I can just go in this direction. I move here to minus A. Okay. I can have the plane going like that. I can have the plane going down like this, like this. What will be that plane actually? 1, that is x, that is 1, and this is minus 1, 1, 1 bar. But the arrangement of atoms is the same this or that. I can have go in that direction, I can put 1, 1 bar 1. So, but all of them are called by one family 1, 1, 1, because the atomic arrangement is same thing. What is the atomic arrangement? The atomic arrangement, if you see, this is that plane. Okay. Now, what we would like to see is, go back to this original diagram. See, 1, 1, 1, 1, 1, 1 plane is drawn from there along this diagonal here. So, along the diagonal there on that plane, what are the atoms which are present? Arsenic, arsenic, this is inside, arsenic, arsenic. So, that is why you have got here arsenic, 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 and on this plane you have got arsenic, arsenic, arsenic. Okay. So, that is what you can see here. Now, go back to this now. Okay. So, all the atoms we have marked now, that is, and on this plane, the back side that plane, that is one atom. Once again, that plane you have got 3 arsenic atoms, that line, this line you have got 3 arsenic atoms, and on the back side, that one, it is coming, this is the center of that plane. So, through that when it comes, you get this atom. They are all in one plane. Okay. So, that is what is marked here. So, on that plane here on this triangle, you have got these number of atoms. How many of them belong to that you can see, what is on an average. Now, you also see here at the corner there is one. So, you have got this plane 1, 1, 1 plane, that is totally arsenic, no gallium atom there. You have got another plane which passes through this. You can draw another plane parallel, that is 1, 1, 1. Whatever is parallel to this is 1, 1, 1 family. So, I can draw parallel to that passing through this, that is 1, 1, 1, that is arsenic. In between these two, you have got a gallium plane, correct, because this is A, but A by 4, A by 4, A by 4 if you take, that is that atom, gallium, that is this atom. So, this atom is below that plane. So, if you stand on that plane, draw parallel lines, you will see that arsenic is there, gallium is there, then arsenic is there. So, you can see the forces of attraction between these two planes will be not merely the covalent bonding plus electrostatic force will be there, because this is totally arsenic, this is totally gallium next plane, which is actually, in fact, if you see carefully these planes, this draw these lines, okay, if you carefully see, now this and this forms a, what does it form? Pardon? Tetrahedron. See, what we have is a structure something like this. Okay. That is the top, is the one coming like this. So, you have got all these atoms on the top of that corner and also of course here. Okay. Now, I am sorry, I just have to draw these atoms, just 1 minute, okay, because since these are joined, it looks different. Join these atoms, those atoms, and join them onto this. So, what I am trying to point out is narrowing down to these. These are the 4 neighbors. See, this gallium atom, that is not its neighbor. The one on that side, this one arsenic, this arsenic, this arsenic. So, these are the 4 neighbors for gallium atom, and these lines 1, 2, 3, 4 are the bonds. Okay. Do not worry about this particular, this line I have drawn to show the plane. Okay. In that plane, you have got these 3 atoms which are closest to this gallium atom. Okay. These 3 atoms are closest to the gallium atom. It forms bond with that. This gallium atom forms bond with that one. So, when you draw a diagram in 2 dimension, okay, you saw gallium surrounded by arsenic. I think I will put a slightly color thing for that arsenic. I am deliberately putting that small because tetrahedral radius of gallium is 1.26 angstroms. This is 1.18 angstroms, smaller. Now, you have got arsenic here, okay, this is 31, that is 33, okay, but the tetrahedral radius of these are different, 1.18 and 1.26. This is arsenic, this is arsenic, this is arsenic. So, this is the one which forms, these are the 4 neighbors, which are, just go back to this gallium atom sitting here, bonding with that atom, and that, and those atoms are in that plane, the corner one, this is at the corner. So, these together form the tetrahedron. So, when you say the crystal structure is tetrahedron there, what you have gone is, you have gone into this cubic cell and picked out those neighbors which form the covalent bond together. So, that is tetrahedron structure. Okay. I do not know whether you are able to visualize from here to here going into that. 4 in the side like this. Supposing I have a structure like this, those are the 4 at the top, and then coming down like this. This is the corner, arsenic, 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 arsenic. Where is the gallium atom? Center of this thing, that is there. That is forming bond with 1, 2, 3 like that, up, this one down. That is shown here. It is a bit involved, one has to actually visualize and see, but if you understand the position of the atoms, it is very easy to look into that. So, you have got tetrahedral structure for gallium arsenide, silicon also. In silicon, all of them are silicon, this is also silicon. So, that is where they say it is sitting at the center of the tetrahedron, one silicon atom. Here a gallium atom is sitting at the center. It is not necessary that gallium is sitting at the center of the tetrahedron, it can be arsenic with the 4 around that. Take a look at this now. In a 2-dimensional picture, we can draw it like this. Let me draw it a bit closer so that I can cover more number of atoms. Let me draw arsenic, okay, arsenic, arsenic. So, move down now. On this side, what will you have? Gallium. gallium is surrounded with 4 arsenic atoms in this picture. If you move away, you will see again gallium, gallium, arsenic, gallium. And here this gallium has 4 neighbors which are arsenic. This arsenic has 4 neighbors which is gallium. Gallium. So, that is complete picture. This gallium has got 4 neighbors which is arsenic. That is 2-dimensional picture, that is simple to see. In fact, if you see the 3-dimensional picture, if you go anywhere you pick up, you will see them like that. So, this is arsenic. So, this is arsenic. I can go on. Arsenic, arsenic. I don't know if write up is clear here. Arsenic, arsenic. This is arsenic. Okay. If you want slight difference in color, you can put that. So, to make it visibly that it is arsenic here, arsenic here, arsenic here, arsenic here. So, you can keep on expanding and put gallium here, put gallium here, etc. I can spend the whole hour doing that. The idea is that you have got the gallium atoms surrounded by arsenic atoms and arsenic atoms surrounded by gallium atom. That is the whole idea. Whereas in silicon, you draw the same structure with everywhere silicon. Now, you can see that bonds are like that, 2 you put to show that it is on an average 2. In silicon, you put 2 like that, total 8 electrons. And these are the electrons which you represent, which form the bond. Now, arsenic is having 5, therefore, one of the electrons will be slightly displaced partially towards that. Okay. So, it will be having slight electronegativity, negative charge on arsenic and positive charge on gallium. Now, that is the reason why when you go down like this from this 111 plane, you go down not a by 2 or so, it is some root 3 by 2, root 3 and 1 is to root 3, that diagonal if you go. So, if you go down into this plane, that plane has all gallium atoms which has got plus hard charge and next one has got negative charge. So, you can see these atoms are the planes are holding each other with that attractive force. Whereas, if you take 110 plane, there is no additional binding force. It is only the covalent bond, there is no electrostatic force. This is one difference that you remember, it has some effect. It has got a very important effect on etching, cleaving of gallium arsenide. For example, if you take silicon, if you just break it, what is the cleavage plane? 111 plane. That is mainly because there is no other binding force there. It is only covalent bond, okay? And it is 111 plane because along the 111 plane binding is good because that is densely packed. Number of atoms along the 111 plane is more, that is densely packed. So, that is why 111 plane when you cleave, it does not break along across that, it is parallel to that, it is coming off, okay? Because that plane as it is bound together. If you take gallium arsenide, the cleavage plane, can you take a guess? If you take 100 plane, you have gallium arsenic, gallium arsenic. That means there is force of attraction between the two, in addition to the usual bond. If you take 111, it is gallium arsenic, gallium arsenic. Again, that force of attraction, electrostatic force is there. It becomes difficult to tear. If you take 110, we saw it totally number of arsenic atoms equal to number of gallium atoms in that plane, this plane. you saw that number of atoms counted together, you see 6 here, but contribution is only 2 and gallium atoms 2. So, if you take the entire plane, number of gallium atoms equal to number of arsenic atoms, charge neutrality. Between the planes there is no electrostatic force of attraction, it is only covalent bond. So, it becomes easy to cleave in that plane. Okay. So, between the planes binding is not so hard, so we are able to cleave it. So, the cleavage plane, okay. Now, let us take down, just write down some of these facts. One plane alternate this is very important because they make use of this property for some technology. Alternate gallium plane and arsenic plane. This is true whether you talk of gallium arsenide, gallium phosphide or gallium nitride. So, to keep it general, they will call it as 1 A plane, 1 B plane, B referring to 5th group, A referring to 3rd group. So, A plane, B plane. Okay, one on A plane has gallium, one on B plane has arsenic. So, there is force of attraction due to the ionicity, ionic bonding, weak ionic bonding, slight ionic bonding there is electrostatic force between these planes. Okay? But I have said I have just put in black and white or black and green. Okay? Now, if you take 1 1 0 also similarly, 1 1 0 0 planes also have net charge. Net charge, okay, and hence net force of attraction, electrostatic attraction. Okay. Electrostatic force of attraction. So, it becomes difficult to cleave them in those planes. Okay. This makes it, this property difficult H and cleave in these planes. Okay. There are of course other corollaries to this. In general, there is a thing. So, particularly is true for the cleavage. Okay. Now, let us take a look at the other planes which have been staying all the time. Okay. I have removed it. Just show. If you take a look at 1 1 0, 1 1 0 plane has equal number of gallium and arsenic atoms. Therefore, net charge on this plane is 0. Therefore, no electrostatic. So, therefore, electrostatic force, bending force between the planes, these 110 planes is 0. Therefore, EC to cleave along these planes. Therefore, it is easy to cleave along these planes, because that is the key thing. When you say, therefore, whether it is gallium arsenide or indium phosphide, the cleavage plane is 110. Okay. So, (110) is the 110 is the cleavage plane. In gallium arsenide and indium phosphide, and related compounds. Ternary, when you make gallium indium arsenide, that has a cleavage plane which is equal to 110, and the related planes, related compounds. Okay. So, this is what I want to drive home, because the entire idea of taking a look at this crystal structure is to understand some of the properties which are relevant to technology. And what is relevant to technology is, if I scribe and cleave in silicon, it will cleave along 111 plane. Okay. How do you cleave? You just draw a line, scribe to a depth of about 1/10 of the thickness of the wafer. Then just apply a little bit force, it will just cleave along that plane. That is what is meant by the cleavage plane. If you just drop it, it will cut into pieces which are, if you take 100 wafer, it will be having that type of shape, that is corresponding to those triangular, for example, or the edges will be 111 planes. So, if I take a 100 wafer, that is just one or two things related to that, because we can't get into new topic, but at least this has a profound influence on of technology. So, let us take a look at that. I have many more properties related to the doping, etc. We can see it subsequently in our next lecture, but some of the things related to this I will try to discuss. If I take a 100 plane x, y and z, 100 wafer. Okay. What is the wave plane? XY plane. or parallel to xy plane. I can say parallel to xy plane, or strictly speaking you will say it is parallel to any one of those x y or y z or z x. Now, I just take this. If I take the 1 0 0 wafer, okay, the surface is parallel to this. Now, where will the 1 1 1 plane be? See that the 1 1 1 plane is at an angle of 54.7 degrees. So, 1 1 1 plane intersects 1 0 0 plane at 54.7 degrees, and it intersects it here. That is called 1 1 0 direction. That is 1 1 0, because a line drawn perpendicular to that is 1 1 0. So, it is 1 1 0 direction, that plane. So, it intersects there. So, if I just draw a line here parallel to that, just cleave it, if silicon, it will cleave along that plane, it will cleave along this plane, which is making an angle of 54.7 degrees. So, if you see the wafers, when you dice them into individual chips, you scribe them, make small chips which are 1 millimeter by 1 millimeter, you see the edge of those in silicon, that will be at an angle. Okay. It can be like this or like that, because after all there is a plane like this or also going down. So, depending upon which way it has force has come, you will see it is going like this or like that. What will happen in the case of gallium arsenide, indium phosphide, etc.? If I take 1 0 0 wafer, if I cleave it, what happens? Cleavage plane is 1 1 0. So, if I cleave it, if I cleave it, this is the 1 0 0 plane, and 1 1 1 0 1 1 0 plane is the cleavage plane, that is perpendicular to that. That is perpendicular to that. What will be the impact of that on the chip or the device? Let us draw that. Let us draw that. See, if I take gallium arsenide, 1 0 0 wafer, 1 0 0 wafer if I take, and then cleave, you get a plane which is like that. I draw a line, I take a wafer, scribe like this, each one is a chip in the scribe and cleave. In the case of silicon device, this is the one which you take out, that will be like that on the top, but if you see the edge, it will be cleaved. Okay. Whereas, if you take gallium arsenide, okay, and if I cleave like that along this, the chip will actually be like this. Oh, I am sorry, the chip will be like this, perfect cube, or it is not cube, it is square vertical faces. So, there is no shape like this. Now, you may ask, what do we care? Why should I worry about that being vertical? In microelectronics, you may not worry, because in microelectronics, what all that happens is here. But when you go to make a laser, you want that plane to be where the light is coming out, that should be polished and to be vertical. So, when you want to make lasers, this cleavage plane which is being perpendicular to 1 0 0 helps you. So, in fact, you can have those surfaces which are shining and which is giving that laser in that plane. So, for making laser diodes, this property is very useful. The property that 110 plane is perpendicular to 100 plane. I can scribe along the 110 direction like that, both are perpendicular, 110 and 11 bar 0 on the xy plane. Both you call it as 110 direction, 110 direction, 110 direction. If you call 110, that may be 1 bar 0, they are perpendicular. So, there the planes are vertical, and that is the key advantage of having this material for this application. Now, I think more or less we just have completed about the crystal structure and its importance, cleavage plane, etc. Okay, and its profound effect on the chip size, chip surface, and its usefulness on optoelectronic devices, and also the atoms being 10011, etc. also we discussed. This particular thing also is the other property which we have seen already, that is silicon is indirect band gap, gallium arsenide is direct band gap. I think what I will do will be next class onwards we start discussing about the dopants in gallium arsenide and indium phosphide. Whatever we talk for gallium arsenide holds good for indium phosphide or for any other 3-5 compound semiconductor. So, we will discuss next lecture about those aspects.